So we'll take where we have left from the previous session. So we were discussing LU decomposition or LU factorization. So in this, if you have a matrix, so you had matrix A. So you know, by elimination, what you can do is you can get something of this sort. So you had this AX is equal to B. Okay. So once we keep on eliminating the things over here, so you will get this U, and then you will get this UX is equal to somewhat say, and this is your U was your say upper triangular matrix. So this was the upper triangular matrix which you got by using elimination. So that's what you did so far. And after this, I told you one thing that we were doing. So we said, suppose if you have a matrix, so you have a matrix 1 4 8 2, something of this sort. So now in Gaussian elimination, what will you do is you will select a pivot. The first pivot is this. So once you selected this pivot, so whatever comes beneath it, so you will make it 0. So how to do that? So you will say take this row 2. Okay, so first row 2 minus 8 times of row 1. So this is what you will do. So you will multiply the first row with 8, and then you will subtract this thing from the row 2. So what will happen as a consequence of this is this. So you have 1 4, you will do nothing to this, and now you are saying 1 4, you have R2, that is 8 2, and now you will multiply this with 8. This will be 8, the first row, 8 1s are 8, 8 4s 32, and you are subtracting this. So you will get 0 over here, because that is the purpose that we multiplied this with, and then you have this 2 minus 32, you will get minus 30 over here. But you know that this operation, if you see, this operation also can be converted into elementary matrices. How can you do that? So you have this matrix 1 4 8 2 over here. So what you can do is you can say the first row I don't have to touch it, so I'll say 1 of the first row and 0 of the second row, but second row I have to check it, so I have to somehow change it because I have to make this entry 0. So I'm saying take 8 times the first row, negative 8 times, because you have to subtract, and 1 times of the second row. So if you multiply these two things, so you should be landing here. So that means every elementary operation that you are performing, so this was an elementary operation, this one. Okay, so it has an equivalent, what is called as elementary matrix. So elementary operations have corresponding elementary matrices. They have elementary matrices. And let's do it now. Suppose if I multiply these two things, you will see that we will land at this. So let's suppose you multiply this. So this will be 1 multiplied 1 and 0 multiplied by 8. So you will have suppose 1 over here. So again, if you take this row, and then this will be 1 by 4 4, and this will be 4 over here. And if you take this now, you multiply this with this, so this is minus 8 and this is plus 8. So you will have 0 over here. So you will have 8 4 32, and then you will have 1 2s are 2, so this will be 30. So you see, you got the same thing over here. So once you perform, either you can perform operations, or the second thing is you can perform this elementary, you can have an elementary matrix and then multiply with it. But the amazing thing about this elementary matrix is that it's finding its inverse is quite easy. So why? Inverse is basically if you have a matrix, it is doing some transformation. So there should be some other matrix which will undo its transformation. So if you have this 1 0 minus 8 and 1, so what is it doing? So it is taking the second row and it's multiplying the first row with 8 and then subtracting that from the first row, or subtracting that from the second row. That's what the meaning of this is. So what I can do is I can say that, okay, can I do reverse of this? The reverse of this will be, you take this R2, the second row. Okay, so you take this R2 and add it plus R1. So whatever we did over here, if you see this operation, R2 minus 8 R1. So the reverse operation of that, or inverse operation of that will be R2 plus 8 R1. Okay, so you'll get back 8. This is equivalent to this. Initially you did R2 minus 8 R1. Okay, so what you are doing is you are again taking the answer and you are taking this plus 8 R1. So if you cancel these two things out, you are getting back this R2. So that means operation this R2 minus 8 R1. So this thing is inverse of this. So R2 plus 8 R1. And you know that this operation also will have a corresponding elementary matrix. So that's what I want to conclude here. So if you want to invert this, you will say 1 0 8 and 1. So you just change the sign. So that's the beauty about these elementary operations. So how did we reach LU decomposition then? So to that I said, suppose you have this matrix A now. So if you see this matrix, so this was our matrix initially. So we had 1 4 8 2. So we had 1 4 8 and 2. So how did we convert it into upper triangular matrix, that U matrix? So we multiplied it with elementary matrix. The elementary matrix that we had is over here. So 1 0 minus 8 1, 1 0 minus 8 and 1. So we got an upper triangular matrix. The upper triangular matrix that we had is over here. This is 1 0 4 and 30. 1 0 4 and 30. So this is our U. Initially this was our A matrix. Okay, and this, if you see, is our upper triangular matrix. Why upper triangular? Because you see below diagonal elements are 0 and upper diagonal are non-zero. So you can see, you can call this an upper triangular matrix. And now if you see this was suppose E1 matrix, the element transformation that you performed first, or we can call it, because we had this pivot, this can be called as E11 because the first element was taken as pivot, and we can call it E2, or you can just call it E1. E1 basically means the first elementary operation that was performed on this. Now what we can do is, if we apply inverse on this, okay, if we apply E1 inverse, so you know what that is, okay, you just have to change the sign over here, and this will be E1 and this will remain A. Okay, over here what will happen is you will get E inverse of U, because I am taking E inverse on both sides. Now you know that this will be identity, so till over here this will be identity, and this will be my A, and this will be my E inverse of U. So what you have got now is A is equal to E inverse E1 of inverse of U. If you see this E inverse, this one, the inverse of this, so you had 1 0 minus 8 and 1. Okay, the inverse of this was 1 0 8 and 1, and this is an upper triangular matrix. It has these diagonal elements are 1 1, and below diagonal elements are 0, below diagonal elements are non-zero, and upper diagonal elements are 0. So this is the lower triangular matrix. So this is lower triangular matrix. So that's why instead of this E inverse I can write L over here. That's why I can write A is equal to LU. Okay, you can do the same thing for 3 cross 3. If you say you have a 3 cross 3 matrix, so then what you will have is, you will have initially say one pivot over here, then you will have second pivot over here. So accordingly you will take, say you have this A matrix which can be n cross n, then you will have E1 first pivot, you will have E2 second pivot, you will have third pivot, and so on till suppose any number of pivots. So what you will get is, you will get an upper triangular matrix as a consequence of this. Now you know that if you sort of take this matrix, if you take this E1 and you can invert it easily, okay, because you have to only do one thing, that is you have to change the signs there. So once you change the sign, so what you can do is, you can say that I have this E3 inverse, E2 inverse, if we have 3 elements, and E1 inverse, that is U, and if you multiply these things in this order, so you will get what is a lower triangular matrix, LU. Okay, this should be clear so far. Any questions still here? To clarify it more, let's take a 3 cross 3 example, and we'll see that if we can multiply these inverse together, you will get a lower triangular matrix. Suppose we have this A, so A over here will be 2 4 minus 2, so I am taking this example directly, 1 3 1 1 3 and 0. So now you have to factorize it. So what you can do is, you can do 2 things. This is your pivot, and these things have to be made 0. So what you can do is, you can take row 2, and you can say row 2 minus 4 by 2 of row 1. Okay, and then you have this row 3 again, so row 3 will be row 3 minus I think row 1. This is 2 times of this, 2 times of R1, and this is row 1 if you take it like this. So now once you perform these operations, so we will get some matrix. So let's call it U1, the upper triangular matrix 1. It's not for fully upper triangular, but let's call it U1. So this will be 2 0 and 0, because we made sure that these two entries are knocked off. And after performing the calculations, this will be 1 1 and 2, and this will be 1 1 and 1. That's what we did. Okay, then the second step in the elimination. Second step in the elimination is, you have to now take this as pivot. Okay, and then after that what will happen is, you will knock out this entry over here. So R3 will be equal to R3 minus twice R2, something of this sort. So now the last matrix you will have U, that actually is a lower triangular matrix. You will have 2 0 and 0, and this is 1 1 and 0, and this is 1 1 and minus 1. That's what you will get over here. So if you see, this is your U. Now what you can do is, you can build L from here. So what you have to bring this lower triangular matrix. So lower triangular matrix can be built from these operations, because these element transform, as I said, you have to just invert them. Okay, so you can even say, well, what's the multiplier over here? So the multiplier over here was 2. If you see, the multiplier in this case was suppose 2. The multiplier in this case was say 1. If you keep a track of these multipliers, you only know that we have to get, sorry, this was minus 1. Okay, because you had this minus over here. So over here, if you see, this is 1. Say again, if you see multiplier in this, so multiplier over here again 2. So you have this 2 as a multiplier. So what you can do, if you keep track of these multipliers, you know that if I have something of this sort, 1 4, say we had this 1 0 4 and 1 minus 4 or 1, something of this sort, you will just change the sign. If I keep track of this, this will be my multiplier, because that is what I am multiplying this with. So I can directly create these L matrix. So if I tell you this, so L is equal to, this L will be 1 0 0. So what you will do is, so you will have a multiplier over here, you will have a multiplier over here, you will have a multiplier over here, and 1 and 1, and then we'll have zeros over here. So that's how this will be an upper triangular matrix. And you have already kept a track of these multipliers, so you can just fill them over here. So multipliers will be 1 2 and minus 1, 1 2 and 1 0 0 and 1. Sorry, this is 0. and this is again 1. So 1, 2 and minus 1, 0, 1 and 2. This is 2. This is 0, 0 and 1. So this will be my lower triangular matrix. So how did I get to this? Because I have to just keep track of multipliers. I'll have, suppose E1 will be there, say I'll have E2 will be there. So I'll just reverse their order. I'll say E2 inverse multiplied by say E1 inverse, and what I'll get is I'll get this. So that's why I'll just keep track of these multipliers, the multipliers that I had over here. So these multipliers were my multipliers, and I'll just fill these entries over here. That's how easy it is to find this LU decomposition. So whatever elimination you are doing Gaussian elimination, you are having this matrix A and you were converting this into U. Okay, as a consequence, because you were performing some operations, you are getting a set of elementary matrices. So you had this E's, so you applied in reverse order, and you just have to keep track of these multipliers. So at the end you will get this LU. So A is equal to LU. But there is one condition. So one condition is there were no row exchanges. No row exchanges were there. So why do we need row exchanges? Because suppose if there is a case where your pivot got changed, suppose you had this 1 and say 1, 2 and 3 was initially there, and then this was 2 and this was say 4 and this was 9 and 0, 5, 8. Suppose once you are doing this, so if you knock out this variable and if you multiply this with 2 and you will knock out this variable, you will see that this also will get 0, this will become 0 and this will also become 0. So now what you have also done is you have made a pivot 0. So now there will be a row exchange. You have to, in order to perform Gaussian elimination, okay, you have to perform a row exchange. So even if there are no when there are no row exchanges, you can directly say that I can do this A is equal to LU factorization. I can factorize a matrix into a lower triangular matrix and upper triangular matrix. But there should be a condition that no row exchange should be there. But if there is a row exchange, what to do then? There is a big question. Okay, if we have to perform row exchange, because now this is not there. So if this pivot was gone, so we have to perform a row exchange. So we have to again do one more thing. Okay, we'll come to that. We'll come to answering that question now. Any questions so far? So before coming to this question, that how can we solve this if there is a row exchange? If one pivot got knocked out, so we have to make row exchange, and then we will be able to bring up that lower triangular matrix. So we'll put this question on hold. We'll first see why is it important. Why is this LU factorization important? So I'll first show you one way why is it important. So you can easily solve a linear system of equations by using this. Why? Suppose you had this. You had AX is equal to B. This was your case initially. So instead of doing elimination on A and B together every time and we factor in, so what we can do is, rather than this, we can say A is equal to LU. Assuming that there are suppose no row exchange for now, then we can say this. We can have this L C is equal to B, and then we can have this U X is equal to C. So once you have these things, you can do forward substitution over here. You can have forward substitution, and you can have backward substitution over here. You can solve the equations. So by that I mean, suppose if you now have this like lower triangular, you will have the C is equal to B, and then you will have this upper triangular matrix, and then X, this will be equal to C. So what you can do is you can easily do a forward substitution over here. You will solve these two equations, one by forward substitution, one by backward substitution. Let's say we have this. We have U plus 2V, and then we have 4U plus 9V. So this is equal to 5 and this is equal to 21. So I am taking these values directly. So suppose my A is like this. Now if I take coefficient matrix, so A will be equal to 1, 4, 2, 9. So this is my 1, 4, 2 and 9. And now I have, say if I LU decompose it. So what I can do is the LU decomposition would be 1, 0, 4, 1. Okay, this is my lower triangular matrix, because once I perform this, I'll multiply this with 4 and then knock out this variable. So I'll get an upper triangular matrix over here, that is 1, 2, 0 and 1. So this is my A, this is my L and this is my U. Now what can you do is you can solve this LC is equal to B. The first thing that I told you for here, LC is equal to B, and you can do it by forward substitution. So what is your L? So your L is lower triangular matrix 1, 4, 0, 1. Okay, and then you have this C1, C2. So this will be equal to 5, 21. Okay, you can easily solve this. So you'll get, because you have already knocked off this variable, you can directly say C1 is equal to 5, because you have one of this. Say once you multiply this, you'll directly get that C1 is equal to 5, because 0 of the second C2. So directly C1 is equal to 5. And then for this, you'll get 4 times 5 plus C2 is equal to 21. Okay, this is what you will get. And this is 4 5s are 20. Then you get C2 as directly is equal to 1. So you'll get C1 and C2 values you got there over here. C1 and C2 values, one is 5 and one is 1. Now you'll solve UX is equal to C. So what is this UX? UX, you know, 1, 0, 2, 1. This was my upper triangular matrix. And what is X? So X in this case is UV. So that's what I'm solving. So this is UV, and now I know this is equal to 5, 1. Okay, the values I got over here. So they basically C1 and C2, or is it 1 5 or 5 1? So I had let me check. C2 is 1 and C1 is 5. Yes, this is 5 1, correct. So now what you can do is you can see that we have already knocked out one variable. You can directly get value of v over here. So value of v, if you see, is equal to 1. So v is equal to 1 directly because you have a knocked out variable over here. So once you solve this equation, you will get the value for u as well. So the u value will be 3. So you solve the equation. So here's the solution. So if you had this 2 cross 2, if you had this what we have two variables, two equations. So what we did, so we performed this elimination. So but what you did, you directly took this L and U. You had this LU decomposition. So from this LU, you said, let's say LC is equal to B. So you know what B is. So this was over here. So this is L and this is your C and this is your B. You are first trying to find C1 and C2. You found this C1 and C2. Now you know that this UX is equal to C. So then you can directly see that this is your C and you can solve it for U and V. So what you have to do is you perform Gaussian elimination to get L and get U for this matrix A, and then easily what you can do is you can solve for X and Y. This is one of the applications, and other application that we have discussed is that the factorization is a very important concept. If you have a bigger matrix, you can factor it in a different way, but this algorithm that I directly showed you over here, this is actually used by your NumPy, Python and stuff. So when you are asking it to say solve linear equations, it is not using some other method, it is using this method. It is using LU decomposition. So it performs this. It first gets a lower triangular matrix and upper triangular matrix, and then what it does is it will do forward substitution and a backward substitution, and from there it will get the solution to your equations. So that is how it is done in MATLAB, the software that you have. Most probably that's how it is done in NumPy. Okay, and there might be other methods that they might be using, but this is one of the methods to solve the linear equations. And you know the fundamental question or fundamental problem in the algebra is to solve linear equations. So that's why we are doing this LU decomposition. And the other reasons I told you that there are a lot more applications of factorization. So if you factor the matrices, you can there's a field called as AI interpretability. So you will see that the factorizing matrices, because if you see these weight matrices, if you can factor them there meaningfully, you can make the model interpretable. So this is also an active area of research right now, and people use this matrix factorization there. So if I also told you, suppose this is one matrix factorization, LU decomposition. So you will have other matrix factorizations which can be applied, suppose, to recommendation systems, etc. So it has a lot more applications. It's not just to solve linear equations. I'm just giving you a concept over here, but whenever we go to machine learning, deep learning, you will see the deep implications of this concept. Let's now solve the question that we had earlier. So this A is equal to LU under the condition that there is no row exchange. So no row exchange should be there. So if there are row exchange, what to do then? So if there are possible row exchange where a pivot is knocked out or a pivot becomes 0, so we have to figure out a solution. There should be some way out so that we can handle these cases. So to study that, we need to go to what are called as permutation matrices. Permutation matrices. Okay, so what is a permutation matrix? So if somebody asks you what a permutation matrix is, so you can say that, you know, if I have to suppose if I am given, say, 3 cross 3 matrix, I am given 2 4 1 0 2 1 1 2 6, something of this sort. So if I have to exchange rows, if I say, okay, I have to exchange this and this row, so can't you say that I'll do one thing? So I can do something of this sort. I'll take one of the first row, 0 of this row and 0 of this row. The first row remains unchanged. So if I have to exchange these rows, so what I can say is 0 of first row, and then I have to make an exchange. I have to suppose exchange 2 comma 3 or 1 comma 3. So what I will do is, if I do I have this 0 0 1 over here and 1 0 0 over here, 0 1 0 1 0 over here. So what this can ensure me is, this is telling me take 0 of this, take 0 of this and 1 of this. So it is taking the second row over here, if you see. So what is this doing? So it is telling me take 0 of this, take 1 of this and take 0 of this. So do you see that this matrix over here, this matrix that I made, so it is somehow, it was an identity matrix. I just shifted 2 and 3 columns of an identity matrix. So what this does is, it is performing this permutation. It is exchanging the rows 2 and 3. How many of you are able to understand this? Then whenever you want to exchange rows of this, we change the rows in the identity matrix. Can you see this? So if you see this, so this is one permutation matrix. So permutation matrix is basically what you have is, you have an identity matrix and you have a different combination of identity matrices. So that's what permutation matrices is. So if you have to define this permutation matrix, you can say that if you take an identity matrix, suppose we have this identity n cross n matrix. So what you can do is, if you can just exchange its rows here and there. So you will get to know that, okay, all the combinations that are possible there, so those will be the permutation matrix. So in this case, suppose you had this, you had initially 1 0 0 and then 0 0 1 and then 0 1 0, you exchange this, and other thing will be say 1 0 0 over here, 0 1 0 0 0 1, and you can keep on going over here. So it's a simple problem to solve. How many such permutation matrices will be there? So how many such permutation matrices will be? So it will be, I think, so if you have such n entries, it will be n factorial, because 1 2 3 4 5 n rows. So initially you have n ways to choose, but now you chose one of them. Suppose in this case we had 3 rows to fill, 1 row, 2nd row, 3rd row, and all those rows were different. So it is like having a permutation problem. You can initially you had 3 ways to choose. Now once you chose one, you have now 2 ways to choose and then 1 way to choose. So in general, if you have suppose n cross n identity, so how many permutation matrices will be there? So it will be n factorial. So how many of you got this calculation, that it will be n factorial? In this case there will be 6 matrices, 6 permutation matrices for 3 cross 3, 1 2, and then you can even write more of these things. Can you see it? So now to answer that question, I'll introduce one more concept of algebra, that's called as transposes. So but don't miss the line that we are trying to answer the question. So if we have a matrix and if there is a row exchange possible, so how can we do this LU decomposition there? So we are answering that question. For that I said we have to have a permutation matrix. So permutation matrix will do that. But I also want to give you a brief intro about transposes, and after that we'll put the whole picture together, and then we'll write the algorithm of this in one go. So what is the transpose of matrix? So transpose of matrix A, which is generally written as AT or A dash in MATLAB, if some of you folks might use MATLAB, so there you can show this A dash. So what it is doing basically, it is changing the rows into columns or columns into rows. Okay, that's a pretty simple operation. So say if you have 1 2 8 9 2 4, so in order to perform transpose, this is A, and what is the transpose? You can clearly see I have to just make this a little wider, and this will become shorter, 1 2 3. So this is my 1 to 8, sorry, 1 to 8 and 9 to 4. So this is the transpose of this matrix. So how can I write this mathematically? So mathematically I can write, if I have a matrix A, if I have its ij entry, okay, so what is the ij entry of transpose matrix? If I suppose apply transpose onto this, so what will happen is I'll say A transpose of ij, so that will be ji, so that will be ji over here if you take a transpose of this. So whatever is in the transpose matrix, so this is equal to that. So you take an entry, you just switch the roles. Say I have this matrix, so this is my entry 0, suppose 1 1, this is 1 1 entry, this is 1 2, and this is 1 3 entry. Similarly this is 2 1, this is 2 2, and this is 2 3 entry, and this is 3 1, 3 2, and 3 3. I'm just writing it like in very small symbols so that you don't get confused. So if I have to change, so I'll say I'll exchange these two entries, and I'll exchange say this entry and this entry, 3 1 and 1 3. So that's what I do. So if it's a even matrix which is square matrix, so what I basically I'm telling you that if you have a ij entry in transpose, you will change that by ji entry. So transpose of that is this. So that these both of these are equal. So now if I have a matrix of this sort, suppose if somebody tells me, so I have a matrix 1, okay, 4 diagonal remains the same. Okay, if I have to have a matrix, if I transpose that matrix, that will remain the same matrix. So what I can do is I can say 1 4 5, 2 over here, 2 over here also. Why? Because I have to make sure that rows and column remain similar. If I did, this is 8 and this 8 should be over here also. If I am putting 7 over here, this 7 should be over here also. Now you can see that this matrix is a spatial matrix where A transpose is equal to A. This is called as symmetric matrix. So transpose is an operation in which you change rows into columns, or if you have to see element wise, so you are changing Aij by A ji transpose. And there are different operations valid in transpose. If you have this A plus B transpose, okay, so this is equal to A transpose B transpose, you can individually apply transpose onto that, and this all of these properties are left as a homework to you people to prove. This is very easy to prove. So if you have this product AB transpose, so what will happen is it reverses the order. You will have B transpose A transpose. You can numerically check it, or we have also learnt about addition and multiplication. What is the meaning of that? You can also use your intuition and to prove it pictorially. So one important thing is, if you have this A inverse transpose, if you have a matrix and then you invert that matrix, you find the inverse to that matrix. If you take transpose of that, this is also equal to if you initially transpose that matrix and then find the inverse of that. Both of them are equal. So one more property is, if you have a scalar and you multiply it with the matrix and then transpose the matrix, it is equal to that. You have this you take this constant out, you initially transpose the matrix, then take this constant out. This is the properties which you can easily prove. So this is for your homework. So you have to prove these, and very easy. As I said, you can numerically do the calculations and you will arrive at these results for transposes. Or what you can do is you can apply your intuition that you have developed so far, and then you can easily write a visual proof, or maybe you can write an explanation of why is it so. So one thing I would like to suppose show you over here is I will have a discussion is on inner product and outer product. Inner product and outer product. So what is that? What is an inner product and what is an outer product? Suppose if we have this, so if you are performing X transpose of Y, so usually what you have is you perform this WX transpose X plus B. Okay, you always perform this in the neural network. So that is this operation. If you have this operation where what you get is you are getting a scalar as an output. This can be written something of this sort. You have summation of say xi yi. Okay, so this was a vector and this also was a vector. Say this x was a vector and y was a vector. You transpose this. You transpose the x to make it a column, and then you multiply column and a row. So you'll get xi yi. Say I goes from 1 to n. So you'll get a scalar as an answer. So this thing over here that you see is called as inner product. So this is called as inner product. Okay, then what you have is you also have an outer product. You have also seen that. So when we were seeing different ways of multiplication, that time I told you if you can do this, so you have x y transpose. If you can take suppose a column and you can multiply it with a row. Okay, this y transpose, so this was a, and you multiply it and you will get actually an n cross n matrix. So if you have this is 1 cross, this is suppose n cross n, this is n cross 1, and this is 1 cross n. So the resultant matrix you will have is n cross n, and this is a rank 1 matrix. So this thing over here, the thing that you are seeing, this is called as an outer product. Why am I giving you these terms? Because these are concepts that are heavily used in machine learning, and we'll see the implication of these things as well. Just I am introducing for the namesake. So this is my outer product. Whenever you see something outer product, actually it has much more implication than this. I'm just writing it as simple as I can. So if you see over here, this is called as an inner product that I have written over here. This is my inner product and this is my outer product. So the key property now we will see. So if suppose you know for any x and y which have compatible sizes, so x and y, you have a property like this. You have a and then you have this x and then you have this y. So this multiplication should be compatible though. X and y should be compatible. If you apply transpose onto this, okay, this is equal to x transpose a transpose y. Okay, so this is also a property in transpose. That's why here if you see, this is your if you take an example of this sort, suppose you have left side, on the left side you have this ax, okay, and ax, then you have this one, you have this inner product of ax, this is inner product, okay, of ax and then with y. Then right side if you see is inner product of this x and then this is with y. This is inner product also. But if you see what is the inner product, so here if you see this is like this x transpose, if you call this say big x transpose y, so this is your inner product. So this inner product, so we are putting a bracket here, so this is the inner product of ax with y. So on the right hand side the inner product is with x and ay, but you see the transpose got involved. So both of these are inner products, but the way we have written them is different. So this is often taken as this is again sometimes taken as definition of what a transpose is. Okay, you can take an example of this sort and you can see this. So this inner product and this inner product is equal, but you see how transposes perform, and this can also be proven very easily. So I am not giving you all the proofs because I am thinking that you people should develop your own proof muscles. Whenever you are given some statement, you should be able to dissect it down and prove it. But these are the properties that hold. So you see here the inner product is between ax and y, and the inner product here is between x and ay. Okay, this inner product and this inner product is equal, and this is because of transpose, and the proof of this is quite easy. And I also introduced one more concept, symmetric matrices, that is A transpose is equal to A. This matrix is called as symmetric matrix. Okay, now having all of these things down, you now know what a transpose is, you now know what a permutation matrix is, what permutation matrices are. So what a permutation matrix, if you see suppose this, so you see 1 0 0 0 0 1 and 0 1 0, you know that this, you know this also is a permutation matrix. So in 3 cross 3 you have this permutation matrix. Suppose you take a transpose of this, okay, you say this is my permutation matrix, you take permutation transpose. So you take transpose of this, the transpose of this will be 1 0 0 1 0 0, okay, 0 0 1 0 0 1 and 0 0 1 0. Okay, this is one of the examples. So you have P transpose, or you have this P and you have this P transpose. The peculiar property about this P and P transpose, this P transpose also lies in those transpose matrices. So whatever you had P had you had a set of permutation matrices. So this was a set of permutation matrices. So if you take P, if you take any P from this, so if you take any small p which belongs to this set of this, So and then you will transpose that. So you will transpose that P. Suppose you took that P transpose. This P transpose will also belong to P. Did you get my point? So basically the closure property holds here. So closure property. What is the meaning of closure property? Suppose if you have a set of something, you have set over here. So if I take any P over here, so let's consider this T as an operation. This T is an operation. Transpose is an operation. So if I take some permutation matrix out of this, so if I perform transpose on that, the matrix will still lie over here. One more important property about this permutation matrix is that this P and P transpose will give you identity. That is, P is equal to the inverse of P is equal to the transpose of that. If you transpose the matrix, you will get the inverse of that matrix. Did you get my point? So I'm just telling you the properties that this permutation matrix holds. So now what you can see is we have this permutation matrix. Suppose if we have to perform row exchange, we'll multiply a particular, suppose you had this big matrix n cross n, and this was your A matrix. Say this is your A matrix, and it had a lot of pivots where it was becoming 0, and you had to perform these row exchanges. So you had to perform these row exchanges. So what I said is now, so in at the end you will have to perform a lot of permutations. Suppose row 2 pivot became 0, and then you will exchange it with some row, and then again some other row became 0. So you'll have a lot of permutation matrix. Initially you will apply one permutation matrix. Suppose P1 which will convert say 2 to 3, which will cover 2. Suppose something of this sort, 2, 3 rows are exchanged. Then there will be other permutation matrix applied to this P. In order to remove that pivot from that place, suppose the 5th row was sort of swapped with 8th row, something of this sort, and you'll have a lot of permutation matrices. So when you multiply these permutation matrices, what will happen on this? So you will again get a permutation matrix that will still lie on that. The closure property holds on transpose as well as on this P. So if you multiply these two matrices together, you will still get another permutation matrix. So can I write something of this sort? Because I had this A which was equal to LU. Now this is not only A. So what I am doing is I am applying permutation sometimes. So I can apply all these permutation in one go. So I can say I applied this permutation first, then this permutation, or some other permutation. So I even applied, say I exchange 1, 2, 3, 4, something of this. So I can write. So I have a P matrix at the end. If I multiply all these permutations together, it will again be a permutation matrix. Okay, it's like having that Rubik's cube. You are performing a lot of operations. So now what you can do is I can write it something of this sort. So this tells me that you can solve any, if you have any A, you can break that into LU, but you should properly know this P. You should know what this P is. So if you know this permutation matrix, okay, then you will do this PA and then you will decompose that with LU. So nothing will get changed because each of the row in this is like having a one equation. So A, one row is equivalent to one equation, second row suppose is second equation. If you exchange the rows, it doesn't affect, because anyway at the end of the day you are solving a system of linear equations. That is what you have to do, and in this case you have this PA is equal to LU. Okay, the key concept that we studied was, so first initially we studied our transpose, then we saw the product of transpose, inverse and inner product, outer product and symmetric matrices. Then we saw that this is the most generalized way. This is the generalized way of decomposition. Why? Because sometimes it might not be possible to directly break into LU, as there will be row exchange, so that will create a problem. So what we have to do is we might have to perform this row exchange. So what we'll do is, in order to remove that row exchange from this, we'll initially multiply this A with this P, so that we will just exchange the rows upfront. After that, what will happen is we can convert that matrix into LU, and whatever good things this LU is giving us, so we can make use of that. Okay, so let's do one exercise at the end of this now. So we will code this algorithm. So we'll code this algorithm. So I'll take here questions. Any questions so far? So what we'll do now is we will first write a generalized algorithm. How do we perform? How do we do this LU decomposition? What is the core algorithm? And then we'll code it up. So what you can do is, so I'll write this LU decomposition core algorithm. Okay, that's most probably what your packages are doing when they are doing this decomposition. The first thing is for each of the columns. So for we have, let's suppose we have these pivots. So we have the initially you will select a pivot. So 1, 1, 2, 2, 3, 3, 4, all of these are your pivots. So you'll find the first step that you do is you will find a row which has the largest pivot that at that place. Like suppose if you are performing the first step, so you know you have this matrix and you are performing this is a pivot. So you will select the pivot which is the largest element in that. Why so? Because you know that computer can only have a finite precision. So for that precision problem, you would not like to have a very small number over here. So if the small number is here, it will create some precision problem. So you would want this pivot as big as possible. That's what you will do over here. So you'll find a row first. So every time you will find a row from the k downwards. So suppose if you are on kth pivot, so initially you have one and second pivot, third, fourth. If you are suppose at fourth pivot, So whatever is beyond, like below 4 downwards, you'll go 4 down, and whichever is the largest number in that particular column. So I'll take an example. So you have this. These are your entries. So yeah, you are right now in the say 4th iteration. You are solving 1, 2, 3, 4, something of this. So say your pivot is at this place. So what you will do is you will take this column. So beneath this, whoever is the biggest element, you'll perform that row exchange. Why? As I said, because of precision problem, you want the pivot to be the largest element, so as to have this precision accuracy. So that's what you will do that as the first step. So find the row, that is the row that I'll find is k downwards. You understood what I mean by that? If I am a kth pivot, so I'll go downwards. So whichever row has largest value, so find that row k downwards with the largest value, okay, in that particular column, in column k. If you are in 4th suppose pivot, so you are finding that go all the rows down and pick up that row, swap that row which has the largest number at that particular column. And then second thing is you have to swap the row into position, into k, okay, and then you also have to record it. Why? Because you also have to see what permutations are added. You also have to record it. So swap the row into this into position k, and then in this u. So because you are making upper triangular matrix, so in that you will swap it, and then you also will record it, record the swap. That's what you will do. This is the second step. And the third step is again, so adjust the already computed columns in L. So because you are making this U and L, because you have to keep you have to bring those entries, that L1, the entries that I told you, because you are parallelly making two things. You are making L, U and P. These are three matrices that you are constructing, okay, because you have to get values from X and Y. So how are you getting U? By producing Gaussian elimination. How are you populating this P? Because you are keeping the track of which row exchange I perform. And how is this L performed? So once you perform in a Gaussian step, so you keep the track of this L and you are populating that L as well. And again, step third would be adjust already computed columns in L. Columns in L to reflect the swap. So this is what you have to do. Okay, and then for each of I below, and you have to and you know how to perform Gaussian elimination. After this, you will perform Gaussian elimination from this onwards, Gaussian elimination. And you know how to do that. So how to do that is you find a factor, and then I think this already was done in one of the lectures. So below this you have to perform Gaussian elimination. But because of this PA is equal to LU, so you have to perform these steps. The first step is, so whatever pivot you are at, you have to find the largest pivot in that column. Say I am doing the first step, so I'll look for I'll look in every of this column, and I'll see which has the largest value. Suppose row number 5 has the largest value at the first pivot, so I'll swap 1 and 5. That's what I'm trying to do here. Find a row that is k downwards. So if you are at first pivot, so you will see all the things that are downwards, and you will take the largest element over there, and that will have a row, and you will make an exchange. Say if you are second at the second element, suppose you are at second element over here, you will see from second onwards what is the largest element in that particular column. If say in that second column the largest element is at 7th column, so you will swap 2nd and 7th. That's what these two steps do. Find a row that is k downwards with the largest value in the column k. So after you find that, what you do is you'll swap the row into kth position in that, because you are making this U, you are making this Gaussian elimination. By Gaussian elimination you are making this upper triangular matrix, and then you also have to record swap, which swap I did. And how can you record swap? By using the permutation matrix. And then you have this L. So in L, what are you trying to find? You are trying to find these entries. Suppose it's the 3x3 matrix, so you know that this is 1 1 0, this is 1 1 1, diagonal is always 1 1 1, and then this is 0 0 and say 0 over here. So you have to find this entry, and this entry. So these are our multipliers that we saw. So that is what I am trying to tell you over here. So you have to make P, you have to make this lower triangular, and you have to make upper triangular. And after that, once you do all those things, so you will solve this. So you will basically solve PAX is equal to LUX. That's what you are doing. PAX is equal to LUX. This is equal to suppose some PB. Okay, and then once you decompose, once you do this, you will get P, L, and U, and then you can apply permutation on this. You will say for to B dash is equal to suppose some PB, so you will get some B dash. Then you will say LY is equal to B dash, and then you will say UX is equal to Y, and that's what you will get the answer over here. So if I write every step over here, so given that you have this PA is equal to LU, I'm again showing you this because you will get these three things. So what we have is we have to have this PAX is equal to LUX. That's what we were trying to find. So our equation was AX is equal to B. Okay, this A got converted, and because we multiplied with permutation matrix, and you also permute the things in B. So because this PA is equal to LU and you had this X over here. So now what this is equal to? Some PB, because you applied permutation on this. Okay, that PA is equal some LUX, this is equal to PB. So step 1 would be, so you will decompose this A. So you'll obtain P, you'll decompose it in L and U. You'll get these three things. So after applying this, so what you can do is you can apply permutation. You have this B dash now because you have this permutation matrix. You have to change this B accordingly. So you will see this B dash will be equal to, you apply permutation of onto this B and you will get this B dash. This will be step 2. Step 3 in here will be, then you have to solve this. So you will say that Ly is equal to B dash. Okay, and then you have to also say ux is equal to y. And here what you can do is you can do the forward substitution, you can do the backward substitution that we did. You can do forward substitution and over here you can do the backward substitution. So you will get the answer for this. You will solve it for this. Okay, whatever you had, the values you had. So suppose this PA is there, and then you'll get some X solution. Suppose it's a 3 cross 3 matrix, you'll get some value A1, A2, A3, something of this sort. Okay, so let's do that. Let's do this in code. So, but keep this in mind. So this is the algorithm that we will have. So we'll find the largest element and then go downwards. That's the first step, and then we'll swap that and we'll keep that record in P. But you should be clear how did we arrive at this as well. So this is the key step. Okay, the similar thing you have to keep on reminding over here. So because we will have these three matrices P, L and U, and then because this B also got changed because of permutation, you will have to make sure that you apply permutation onto this B, and then you will say Ly is equal to B dash, because you know that how do you get this Y? You got this Y as a consequence of, suppose this Ux, considering this Ux is equal to Y. Okay, and then this Ly is equal to this P dash. That's what I'm doing over here. So Ly is equal to B dash. So why? Because you also performed over here the multiply, that is B dash. That is what you are solving. Initially you are solving, again to give you the view is, you are solving Ax is equal to B. This is what you are solving. Now you know that the row actions are possible. So what you can do is you can say PAx is equal to PB. Okay, so I am applying permutation matrix on both. Now you know that this PA. So what is this equal to? So we can say that PA is equal to LU decomposition. LUX is equal to PB. So this PB can be written easily as B dash. That's what I said. So over here this PB is B dash. So this is B dash. If I consider this to be Y or this to be C, suppose, so I'll say I can write like this, LC is equal to B dash. Okay, and then I know this C, I know this is equal to like UX, something of this sort, that I told you over here. This UX is equal to this Y, this UX is equal to this C. So once you figure this out, so once you have C from this solved from here, so then you can solve this for X. So this is what I am doing over here. Any questions for this? This is a lot of. So fundamental problem that we are solving was this, Ax is equal to B. So what I said is there is a possible way that we can factorize. So we can factorize it like this. A is equal to LU. Once we just had LU and assuming no row exchanges. There is no row exchanges. So when you have no row exchange, what will happen as a consequence of this? So you can say LU of X is equal to B. So this is what I have to solve. So why am I converting this into L and U? Because you know that once you convert something into a lower triangular limit or upper triangular limit, you are knocking out a lot of variables. So I can write this. I can say this UX is equal to C. This Ux, I can substitute is equal to C. So now I can see LC is equal to B. So if I solve this I can easily solve by forward substitution. So if I do forward substitution, so I can get values of C. So I can solve it for C. So I'll get values of C. So those C value I'll use it here, and I can use back substitution. So back substitution I'll use, and I'll find this value of X, and this X is my answer. This is my answer. So this is the first thing that we did. So once I'm explaining, once you have this L, what is the sort of necessity of this, or what is the usefulness of this method? Why do we factorize? So I showed you one example over there where I did the exact same thing. So if you see over here, if you go back a little bit, I said, so in A is equal to LU decomposition, I solved a problem over here. Let me show that. This. So LC is equal to B, UX is equal to C, and suppose I took an equation of this sort, 1, 2, 2, 9, this is my L and this is my U. I said LC is equal to B, so I got the C1 and C2, and I got C1 and C2 as values, and then I said I'll compute this UV value. So this is what I did with once I had this no row exchanges. The same thing I'm saying, suppose now you have this PA is equal to LU. So PA is equal to LU. This is what we are doing. So this is a separate algorithm, LU decomposition algorithm. But we are solving for this, Ax is equal to B. This is what we were solving. But you know that there might be a possibility that there is row exchanges. So what you can do is you can say PA of X is equal to PB. And you know that B this will be changed, so we can write B dash onto this because there will be some permutation done to this. So what I can do over here, because this PA is equal to LU, this is LU of X is equal to B dash. So I can again say this ux is equal to c, call this ux is equal to c, and I can say L c is equal to b dash. So in the forward substitution, I'll get c over here from forward substitution, and then I'll use this c over here, and from backward substitution I'll get this x. So I can solve it for x. Any questions now? So what algorithm is written over here? So this will help us find this p, l, and u. So you know what are the steps over there, and then once we have that, then in order to find the answers to that, this is the discussion that we had after that. So we had this lux is equal to b, and then we'll do forward substitution and backward substitution. We are done with the answer. Let's do that. Let's bring the code window up and we will code it. Okay, if you see this, so what I'll do is I will initially import the numpy. So let me just see, make sure it's working. Yes. So what I can do is I can say, let's say definition LU decomposition. So what will it take as an input? It will take a matrix for which I have to perform this LU decomposition. So I'm doing this. So what I can say is I'll say A matrix. So A matrix is the matrix that I'll have this. So I'll call this A matrix because this is my output as well. I'll give this A is my matrix because I'll do LU decomposition. I'll give P as well. So I'm saying A is equal to NP dot array. I'm converting an NP array and I'm saying it's a float value. And then I'm also getting it a shape because it's a square matrix for which we'll be doing this, because 3 variables, 3 equations. So we have to solve for this. So n is equal to A dot shape. So after that I'll say if this is not a square matrix, there is an error. So how do we do that in Python? So we'll say if A dot shape is, if this shape is not, if the number of rows is not equal to number of columns. So what you can do is you can raise this value error. I hope you are able to see the screen. So after that what we'll do is, so then we'll proceed with the algorithm. So initially I'll create the copies because I have to convert this U and L and P. Suppose I'll do this. So I'll have these 3 matrices: upper triangular matrix, permutation matrix. This is my upper triangular matrix. So this is my A dot copy, and then I'm creating this L and P. These are my identity matrix for now, and then I'll populate these matrices that you have, this L and permutation matrix, because this, you know that it'll be having ones on diagonals, and for this permutation you also know that initially I'll take an identity matrix and after that I will permute, and this U eventually initially it will be A dot copy and then it will be converted into upper triangular matrix. Now what I'm doing is I will start from, for k in range of n, so I'll start from this matrix. Suppose this, oops, so what I'll do over here is, so I will start a loop, the first thing. Okay, so what I'm doing is, so I'm saying for k in range of n, so I'm starting with a variable k. So k will be my some pivot. So initially it will be 0, then 1, 2. It is selecting my pivot element. So what I can do is I have to find whatever is beneath the k. So the algorithm I told you. So have this k element and go downwards and see what is the maximum element there. So whichever row has the maximum element, swap it. Okay, that's what I'm doing is I'm saying which row has the maximum element. So that's what I'm doing. Go k downwards. Okay, so this is max row is k plus argmax of, this argmax is telling you which of the rows has maximum, and you know what argmax is. Argmax is, suppose if I am telling you we have a list of like this, I have list 2, 4, 5 and 8. So if I apply argmax on this, argmax basically means which index has the highest value. So you see this index. So if it is index 0, index 1, index 2, index 3, so third index has, this will give me output 3. That's what how argmax works. If I am giving argmax of say 100, 8, 200, 5 and 6, so this index has the highest thing. So 0, 1, 2, 3 and 4. So this will return me suppose 2, index 2. So that's what this argmax is doing over here. So if you see this argmax, so it is taking the maximum value. So whatever you are giving, the values, if you see over here, you see you are giving absolute value. So you are going u k downwards. So if you see this over here, so this is giving that particular kth row and it is going downwards. It's going that column wise. It's taking kth element and going downward and selecting all those elements from the column. So whole of this will give you that index of that element. Okay, and it will initially, but a given index will be from 0, 1, 2, 3, 4. Now as it is kth element, so it will start from there. So it will add that. Suppose I will explain it by this. So I have suppose this matrix and I am at suppose second index. So I am at a second pivot. So second pivot will be suppose k is my 2, k is 2. So before this, what I can do is I will scan all the elements that are beneath this. And this will be now index 0, index 1, index 2, index 3, index 4, something of this. Say I got index 5 like this. I got index, this is 0, 1 and 2. Suppose I got index 2 over here. But you know, actually this is the row number 4. So what you will do is you will do this 2 plus 2. So whatever you started from, so you will keep that k with you. Because this argmax, once you apply, it will do the argmax value will, it will assign the value 0 to whatever pivot you are currently. That's why I am adding this k onto this. So that's how I am getting this max row number. So once you have this, if it is 0, suppose if the maximum row, comma k is, if the pivot is 0, so that means you have got a singular matrix you cannot solve the equation. Okay, so if you have got this condition, say if u of max row, so whatever row you got, and this k probably, so whatever element you have kth and this max row, that element is 0. Now even after the swapping, the max element was 0. So what you will say is matrix is singular, LU decomposition is not possible. So you cannot have this LU decomposition, you cannot solve it. Probably there are equations which are linearly dependent on each other. So that's what we are trying to check this condition as well. If it is not that, suppose if it is not the case, if max row is not equal to k, so if that we got some different row, we'll swap. Because many of the times we'll get a different row, but sometimes it may happen that the row which we are at, it has the highest element at place. So that's why we are checking this. Max row is equal to k. So whichever pivot we are having. So if there was a element which was higher than it, then only swap. Otherwise, don't swap. So that's why we are writing if max of row is not equal to k, then only swap. So how to swap? So you can swap it like this. Swap the rows in u. So whatever you had, you swap in that. So you say u. I'll make sure that I'll not do any annotation error. So u is equal to k max. So this is how you swap the rows, and then also swap the rows in P, because you have to keep track of permutation matrix. That's what you do over there also. Okay. So permutation matrix, you also have to swap the rows, and then swap only the already computed parts of L. So you have L these, and you also have to swap the only computed parts, whatever you have computed. So if k is greater than 0, then only swap that much. Otherwise, don't swap it, because you are also computing at the same time. You're computing this. So this if is max of this, and this is the third thing. If k is greater than 0, that means you have computed some things in L. So L k max is to k, and swap these rows as well. And then you perform the elimination, and you know how to perform elimination. We have done this in Gaussian elimination. Okay, so what you can do is, so you can come out of this if condition, and you are writing the elimination. You are saying for I in k plus 1, and then you, if this is already 0, continue skip. Otherwise, find a factor, multiply that with the factor, and subtract all that things you are doing over here. So you know this is the elimination step. Okay, you find that value, and then you go downwards all the rows back, and you find that factor, and you have this factor. How do you find that? You know, and then you have this factor, put it equal to this, and then take this factor and multiply and subtract it from the particular row. This is the elimination. And at the end, what you will do is you will return P, L, and U. You will return this. So you will return after the loop is done. So you return this. Oops. How many of you understood this part? So again, I'm showing you over here. I'll go one by one, line by one. So in LU decomposition, what you are trying to do is, initially we have to give A, P, you have to give U, upper triangular matrix, lower triangular matrix, and permutation matrix. So if you see the algorithm, initially we are doing just normal checks, so that we ensure that the matrix is a square matrix, and then you are initializing U, L, and P. These are the three matrices that we are initializing. Then what I'm saying is, you have this max row, because the algorithm says that whatever pivot you are at, whatever beneath elements are there, check all these beneath elements and see if there is the largest element, because the precision thing. So we are doing that, and then if you find that, swap it. So that's what we are doing over here. So max row is perform this argmax beneath the k and see which index has the highest value, and then add that to k. That will be your highest row number, maximum row. That means the row which contains the max number as per that pivot. So if that is 0, suppose if u max row comma that, if that pivot becomes 0, that means somehow, some way, what we have done is, we have a system of equations in which there are dependent equations, and we got entries as 0. We cannot solve it. So the matrix is not, it is a singular matrix. So LU decomposition does not exist. That means we can't have solution for that. Otherwise, what we'll do is, if you even I did not raise this error, then we'll go to this. If max row is not equal to k, most of the times what will happen is, probably there will be a value which will be bigger than the current pivot that you are looking for. So then you only have to swap. Otherwise, you don't have to swap. You have to be on the thing that you are at. So if you swap these rows, okay, so if you have this max row is not equal to k, that means you must swap the rows. So you'll swap the rows in this upper triangular matrix. You'll also do the same thing to permutation matrix, because you also have to keep track that permutation matrix is also swapped. And then you also will do the same thing for L, but only for the entries which you have already computed. So that's why I'm saying, if k is greater than 0, then only this L max of row, and then only you swap these things. And then this is the elimination step. By elimination, I mean you take that row, you multiply it with the factor, and whatever rows are beneath it, so you first find the factor. So you'll find the factor by how? So you'll take whatever row in the consideration divided by this pivot element. So that will give you the factor. So once you have this factor, so you will put that factor into your lower triangular matrix, because we are trying to find those factors in that. So once you this is not even part of elimination. This is part of just filling out that L matrix, and this step is the part of elimination. So if you have this, so what you can do is, you are taking that row now, and you are subtracting it from that row, and making that ensuring that the entry becomes 0. So let's try it out first. So let's see, I have this definition of solve ax is equal to b. Say I have this. So I'm writing definition solve A and B. So I'm giving some equations. So I'll give two arrays to this. I'll give an array over here. So I'll give an array A and B. So then what I'll do is I will perform this LU decomposition on this. So I'll perform this P, L and U and I can print it. Okay, so let's print P. Say we'll print, let's copy this. It's quite hard to type, and let's again paste it. We are saying P, L and U. This is your permutation matrix and this is your U matrix. So because all of these will be used in the solution. So what I can now do is, so if name is equal to main, let's have B also. Let's print this. Otherwise I could also have done this. I'll also set precision. Let me make sure that I copy paste the right thing. This is N, this is your decomposition. Let's do this. Oops. So what I'm trying to name, and I'm first having a matrix A, that is this 2 minus 3 2, and these are three equations, three unknowns, and you have these three things, 3b, Ax is equal to b. That's what I have done. So I'm printing this LU decomposition. I'm printing this P, L and U. So if I directly, even if I don't call this function at all for now, so because that will be used for solution. So if I print this, so what you can do is you can see this P, L and U will be printed. So P decomposition is, so this is your permutation matrix and this is your L matrix, that is lower triangular matrix, and you can see that you have off diagonal elements below it, non-zero, and this is your upper triangular matrix. So you have 0 0 over here, and this is your L, this is your L, and this is your U, and this is your permutation matrix. Okay, can you confirm that you are understanding it? Okay, so if you understood this, so you got this permutation matrix also, you got this left lower triangular matrix, you got this upper triangular matrix as well. So now what you can do is you can solve this. So how to solve? You know how to solve this. This is easy. So I was having this PLU which I was printing here. I'll just delete this line. So I'll use this PL and U as shown to you, because I have to figure out what is the value of X and Y. So now what I can do is, once I have decomposed it, I'll apply PB is equal to this. So this is my PB, that B dash rather. So I can call this B dash also. So this is that P matrix multiplication by B, because I know that these things are numpy array, so I can do this. So this is my B dash, if you remember in the explanation I showed you. Then all I can do is I can do forward substitution and I can do backward substitution. So for that I have to define forward substitution. So how to do define forward substitution? So I'll be given L and B. Suppose for forward substitution I'll define one more method. So over here, before solve, I'll define one more method, that is forward substitution. That will take lower triangular matrix and this B. So how to do that? Initially we'll find length of B, that is we'll keep it in N is equal to length of B, and then we'll say Y is NP of zeros, because that's what we want to find. So this is NP of zeros, and for all the zeros you will do this operation. So this is how forward substitution is done. You can just pause, and this is pretty easy. So you have to return this Y. And similarly what you can do is you can also do the backward substitution. So you can do backward substitution. Backward substitution will take upper triangular matrix and B. So if you see this, so this is your U and Y, you're again doing the same operation, but you're doing it backwards. So you will return X. So this is the actual answer that we are looking for, this X. So after you have these things, after you are solving this, so you have this PLU. So what you will do is you will take this PLU. Oops, I pasted this somewhere else. This is not the correct way to paste it. So what I'll do is I'll just cut it over here and I'll paste it over here, because I'm doing it in solve. So I'm saying PB is equal to P add B, that means finding that B dash, and then I have this B dash now. So once I have the B dash, so what I can do is I can do forward step, that is I will find Y first. Okay, this is that Y, and then I'll find say X, and then I'll return the X. The X is my solution. This X is my solution. So I'll say X is equal to backward substitution and I can return X. This return X is my solution. Okay, so what I will do is if I just remove this part, say if I remove this part, say PL decomposition, you already know this, so even we can keep it. So after that what I can do is I can find the solutions. So let me find the solutions, and the solution would be quite easy, and you'll have to just call this, you'll have to call solve. This thing is to be called definition solve with this A and B, and it will give you the solution. Suppose this is what is called solve, and what can we call it with? A and B, because we have this. So A and B, it will be called with A comma B, the thing that we have, and we can collect the answers in some, say X is answer, so we can print this X. Okay, if I just run it, and we'll see what is the answer. If you see, the answer is 2, 3 and minus 1. Okay, that's it. So you have this P, and I can even print these things. Even just I can remove the print statement. This print statement can be removed, and this P also can be removed. So if I have to solve this, so this is what I am doing. I am taking this A, and then I am taking this B, and everything else gets into solve. In this solve, we are having this A and B, and then I am computing PLU by LU decomposition, and then I am doing forward substitution and backward substitution, and then I am directly getting the solution. Any questions? So if you have any questions, I am still here. Otherwise, we'll stop the recording because we are done for the day.